Can everyone hear me? Okay, volume's good, everything sounds good. Hey, how's it going? Okay, awesome. Good. I will wait just a tidbit more just to see if anyone else pops in, and then we'll get started. All right, I think we have at least a couple of us. Okay, should I wait just a couple minutes or so to see if they join in? Oh, okay, we got another person. Hello. Are there any topics that we should focus on? Do we want to go through the practice exam that she gave, or do we want to start with the one that I made, or do we want to do both? There's this practice final exam that we have from class. We can run through these, and then I have one right here that we can run through as well. And then if you want to go to my website and download this version here that I made, just hit the download link on my website and you'll get this document. Okay. Any preference on one that I should start on first then, if we're gonna do both? Okay, so up to me. I know that she had one problem on her practice exam that was didn't have the numbers listed with the diagram on it, but it's in the solutions. Okay. What I'll do is I'll start out with the one that I made. Okay, yeah, let's do this one for my practice exam. Okay. What am I going to go over today? I'm going to go over all the problems I made on my practice exam. With the time that I had, I made 5 problems, workout problems that we can go through. And once we get through those, we'll go on to the other practice exam if that's what everyone wants to do, or we can just review some concepts, or we can kind of mix it in along the way. Okay. Let's take a look at this one. Okay. All right, everyone ready to go? Okay, let's take a look at the first one, the exam that I made. Again, you can download on my website. This one says hydrogen gas can be electrically excited, ultimately causing photons of various wavelengths to be emitted. This light can be separated through diffraction grating and displayed as what's called an emission spectrum, shown in the figure below. So you can see here that there are a few emission lines here, the purple, the blue, and the red. We're going to look for a couple of things. First question is, it is known that the red emission line, so the one on the far right, is in the lowest energy transition for the given situation, caused by an electron transitioning down to the n=2 state. Calculate the wavelength of the emitted light. So for this one, I'm going to take this back off. I'm going to switch over to this. All right. Hello. Video quality looks good. Okay. All right, let's get started. So for these problems dealing with the electrons transitioning from one energy state to another, there's a couple equations that you can go with. Specifically, if you're looking for the wavelength of the light that's emitted as the electron transitions. So we'll want to use the Rydberg equation. Does this look legible? Bigger, smaller? Okay, looks good. All right. 1 over lambda equals some constant r times 1 over, we can either call it n final and initial, or sometimes they use n and n prime. Sometimes they also use n and m. They're two different energy levels that are used. Let's call this value on the left n prime. Let me know if there's a different notation that she uses in her formulas. That value is squared minus 1 over n squared. Okay. So the context of this problem is that you have some atom. In most problems, this is going to be hydrogen, so it's just going to be one proton in the center. And you'll have an electron that is sitting out in some orbital, like that. So here's the orbital that it will sit in. It's initially in one of these energy states, and it's going to make a transition to another energy state. So what's going to happen is there's one more right here. And the electron will go from one energy state and transition down to the other, like this. And as that falls closer to the atom, so let's say if it goes from an energy state like n=5 or n=6, and it goes down to lower energy states such as n=2 or n=3, you'll have light being emitted. So if you want to find the wavelength of that light, we're going to solve for lambda in this equation. Other things to note in this equation, so for instance, r is called the Rydberg constant. Okay. The value of r is going to be given. It's going to be 1.097 times 10 to the, I think it's positive 7, I think is what it needs to be. I'll double check that 1 second. It's either plus 7 or minus 7. I always forget that. Rydberg constant. Okay, it is positive 7. Okay, yeah, it's positive 7. So this is a given constant in the formula. Now, for the values of n prime and n in this equation, regardless of what you call them, n prime, the one on the left, is going to be defined as the final energy state. And n is defined as the initial energy state. All right. Now, what you'll notice about this in this equation is that if you're going to be looking for a wavelength of light that's going to be emitted, that's going to be a positive value, you need the stuff in the parenthesis to be a positive value. So if you're not entirely sure what value should belong where to which n value, because you'll have two energy states, you'll be transitioning from like 5 to 2, for example, you need to have that the value in the parenthesis ends up being positive. The only way that's going to happen is if you use the n prime value as the lower value and the n value as the higher value. So in other words, if it's going to go from initial being n to final being n prime, then you have to be going from a higher energy state down to the lower one. Okay? So in this particular problem here, so if you take a look at this, okay, notice that in here, in part A, I said for the red emission line here, it is the lowest energy transition for the given situation caused by an electron transitioning down to the n equals 2 state. Okay? So I did not tell you what the other n value was, but I stated that it was the lowest possible energy transition. Okay? So if that's the case, when you're looking at this diagram, for instance, we know that it's going to go down to the n equals 2 state. And it means that it had to start at the next possible energy state, which is n equals 3, because it's the lowest possible transition that you can make down to the n equals 2 state. Now that means in this equation, we're going to use an n value of 3 for the initial, and n prime is going to be 2. And are there any questions on what I have so far with just the setup? Any of this that anyone needs me to slow down on? Everyone seems to be good. Are they going to give us the n values? So basically, unless you're trying to solve for the n value, which is a totally possible question, a lot of times they will give you both of the n values directly. If they don't give you the n values directly, like in my problem, there's going to be enough information to be able to tell you what these values should be, so that you could solve for lambda if that's what's being asked for in the problem. So, also what I'm going to do is I'm going to try to add numbers on every little step I make here, so that if you get confused at any point, you don't have to type out a whole bunch of stuff to try and point me to where I need to be. I'll just start numbering these. So for instance, let me write down 1 here. Let's do 2 for the diagram, 3 for the constant, for these. So if you're confused at any point, just point me to like line number, whatever, and just tell me where I need to go back to. So, okay, so let's find lambda. Okay. So what I'm going to do is I'm going to start by solving for lambda. Right now it's already pretty much solved for, other than you have to invert the value of lambda. So solve for lambda, that's what we're looking for. So lambda equals, so all we got to do is flip both sides of the equation. So 1 over all of this stuff, 1 divided by r, 1 over n prime squared minus 1 over n squared. We have solved for lambda, so what we're going to do is we're just going to plug everything in at this point. Okay. So we have 1 over a bunch of stuff. I'm going to extend this out. R is given. It's 1.097 times 10 to the 7th. 1 over meters is the units. Make sure you pay attention to your units. We have, open parenthesis, 1 over. Okay, so remember that the left value is going to be the final energy value that you drop down to. So remember, this has to be the lower one. So this is going to be 2. We're going to do 2 squared, and then minus 1 over, and again, the lowest possible transition in this case is going to be from 3 to 2. So we're going to do 1 over 3 squared. Okay, so this is line 6. All right. So we have all the values plugged in. All we're going to do is we're just going to run this calculation. Now, I gave you a nice convenient picture, which you may not have, but in my nice convenient picture, I have the red line labeled somewhere around 650 nanometers. So if our answer is roughly on the right track, we should probably get about 650 nanometers, roughly. So I'm going to calculate this part first. So again, notice what happens here is because you have the smaller value of n for the final, 2, and the initial is 3, 1 over 2 squared is going to be a larger number than 1 over 3 squared, so we're going to get a positive value, which is going to help us to get the correct value for lambda. So we have 1 over 2 squared is a fourth. We have minus 1/9 when you square that out. Okay. Get that value right there. We have times the Rydberg constant, which is times 1.097 times 10 to the 7th. Okay. So you calculate the entire bottom, and then you just do 1 over the entire bottom at that point. Okay. And the exact value we get, put it in scientific notation. Don't write out 9 decimal places. The final answer we get for this is 6.56 times 10 to the minus 7th. Notice that the only units in this equation is the 1 over meters here. So because it's in the bottom, it flips up and it becomes meters. Okay. So this value represents a wavelength in meters, so that should be good. If you want to put this in nanometers, all you would need to do is make this be 10 to the minus 9th. So for instance, I could move this decimal point over twice and change that value down twice, because I've made this 100 times larger, so I make this 100 times smaller. So this is the same as 656 times 10 to the minus 9th meters, and we get 656 nanometers. Okay. And that's roughly the value that we expected for the red emission line for this problem. Okay, so that answers the first part. Are there any questions on part A before I continue on to part B? I'll give you a few seconds to digest what we worked through. Okay, you're good. Anybody else have any questions on the first part? I'll switch it back to this if need be. Okay, let me switch back. If we have n values that are far from each other, will the wavelength increase? Okay, so this is a conceptual question. So this is something you probably would see on the multiple choice more likely. So this is a very good question to think about. If the n values are far from each other, will the wavelength increase? So in this problem, the n values are pretty close to each other. So we have n equals 2 and n equals 3. In this case, it's actually the smallest possible transition between the energy levels. As we take the electron and we move it to a higher and higher energy state further away from the center of the atom, it's going to be in a higher excited state, so the energy difference between the energy states is going to be larger. So if you think about if the energy difference gets larger, you have more available energy to emit light. So there is one equation you could use to think about that as well, if you want to reason through that. So for instance, energy of the emitted photon. Okay. Remember that the photon is the light particle. So the energy of the emitted photon is E equals some constant h, it's called Planck's constant, times the frequency f. Okay. So you can also write this as hc over lambda, because there's the equation that relates the speed of light to the wavelength and the frequency of it. So in this equation, we have that lambda is in the denominator, okay? And we have that the energy in the problem, we're going to see what happens to the energy. So if the energy levels were further and further apart from each other, so if we transition from like n equals 20 down to n equals 2, so big energy gap, you'll have more energy, okay? So that means that the wavelength of the emitted light actually has to decrease because it's in the denominator. So a smaller wavelength of light would mean you go from like red to it being maybe like violet, or it could be outside of the visible spectrum. It could be ultraviolet, gamma rays, X-rays. Does that make sense? Awesome. Cool. I'm going to erase the board. Does anyone else want me to pause real quick before I erase it and move to part B? I'll give you about 15 to 20 seconds to chime in before we move on. Okay. Everyone looks good? Okay, let's go on to part B. Okay. Calculate the energy of the emitted light in electron volts. So let's see here. Okay, so how do I calculate the energy of the emitted light? So actually, I didn't even think about part B, but the question that you just gave me, for what happens to the wavelength of the light, we actually just use the energy of the emitted photon. So very conveniently, this is the equation you're supposed to use for the second part of the question. Let's erase the left side. So let's start with this. So part B, energy of light, but we don't want it in the units that we usually use for a lot of things, which is units of joules for energy. another equivalent unit is going to be electron volts, and we use that a lot simply because the energy values for these kinds of things are very, very, very tiny. So you get answers like 10 to the minus 19th joules. So we just use electron volts instead. So in electron volt units. Okay. So what we want to do is calculate the answer in joules because we have all the stuff necessary to plug into the formula to calculate it in joules. But we're going to use a conversion to get it over to electron volts, which should also be something that's given. So if you want to do 1 electron volt, okay, the conversion is actually based on the charge of an electron, so it has exactly the same value. So it's 1.602 times 10 to the minus 19th. So there's your value for basically the electron charge, which is why there's an E in the unit, it stands for electron, and the times 1 volt, so it makes it the same value. So joules. Okay. So this right here is your conversion factor that goes back and forth between joules and electron volts. Okay. So let's start with the equation. So we have E equals HF. I'm going to define H as Planck's constant. That's the name of that. And the value you should be given 6.626 times 10 to the minus 34. It's extremely small. Joule seconds. Pay attention to the units because sometimes they give H in different units. Most of the time it's in joules, so what that will mean is you'll get answers with joules in it. There's another version of Planck's constant that has it in electron volts if you like Google it or something. And if you use the version of Planck's constant in electron volts, you'll get an answer in electron volts. So we're just going to default to this since this is what we use most of the time, and we'll just convert it at the end. Let's give these a couple of numbers. So 1. Okay. All right. So again, because I don't have the frequency immediately, which I could ask you for the frequency first before I do anything, but since I know nothing about the frequency yet, I already know what the wavelength of the light is, which is 6.56 times 10 to the minus 7th meters. I would want this in lambda. So again, I'm going to write this automatically as HC over lambda. Okay. And all we're going to do is we're just going to drop in all the numbers. And then also C, it's another constant. It's defined as the speed of light. And it's equal to 3.00 times 10 to the 8th meters per second. So we're going to plug these values in. So E equals Planck's constant, 6.626 times 10 to the minus 34th joule seconds times the speed of light, which is 3 times 10 to the 8th meters per second, all divided by the wavelength we found in the previous part, 6.56 times 10 to the minus 7th meters. Let's call this 2. And let's calculate this out. So let's do bottom. So 6.56, 10 to the minus 7th. It's in the bottom. Multiply cross times 6.626 times 10 to the minus 34 times speed of light is 3 times 10 to the 8th. Okay. Let me write this answer down. So what we get for the energy of the photon that's emitted in joules is 3.03 times 10 to the minus 19 joules. Okay? You should expect your answers for the energy of the photon to be very, very small. Around 10 to the minus 19, they're very similar values. Okay? If you're getting positive values for the energy of one photon, then it's not good. It's too much energy. Now, what we're going to do is we're going to convert this answer over to electron volts. I think everyone's good for now. Does anybody have any questions on this so far here? Okay, everyone looks good. All right. Okay, so let's convert this real quick. Okay, so if you want to do this in the shortest way possible, or the most intuitive way possible, 3.03 times 10 to the minus 19th joules. Treat that as a fraction over 1. Set up a conversion bracket with fraction. And then you're just going to put the units on the bottom that will cancel out. So you have joules on top, joules need to go on bottom. Okay. You're going to use the conversion factor given. So it's 1.602 times 10 to the minus 19th joules on the bottom. And then we're going to put 1 electron volt on top. This is the correct way to convert to electron volts. So now this is just equal to. Most common mistake to make here, besides accidentally flipping the values where they need to be, is sometimes what you'll do in your calculator is you'll end up plugging this number in, dividing by the bottom, but you forget to put parentheses around this right here. So what happens is you divide by 1.6 and you multiply by that value and it gets you the wrong value. So don't forget to put parentheses around this entire thing. Divided by 1.602 times 10 to the minus 19th. Okay. So the answer we get in electron volts, okay, this equals 1.89 electron volts. Usually the values you'll get for electron volts are pretty much numbers that you can count on your fingers. So values like 1, 2, 3 electron volts, maybe a little bit smaller, but they're relatively same values. Okay. All right, so this is the whole problem. Are there any questions on anything I did here? So I'll label the conversion number 3 and the answer is number 4. Okay. Let me know if there's anything on here before we move to the next question. All right. Everyone seems to be good. All right, let me pull up the next one. Okay. Let's take a look at number 2 on this. Okay. Making sure everyone is good. All right. So for this one, number 2, a piece of metal is illuminated with incident monochromatic light, and an instrument detects electrons which escape the material. It is found that when illuminated with indigo light, about 450 nanometers, no electrons are detected. However, when the metal is illuminated with ultraviolet light of wavelength 190 nanometers, electrons have a maximum speed of 1.00 times 10 to the 6th meters per second. Reference to the table of information below for the metal work functions. So referring to this table right here, they give you all the work functions for all the materials. Okay. Ideally, in one of these kinds of problems, they'll give you the work function for a given material. If it's not, if they don't give you it, it might mean that you might need to solve for it. First thing we're going to do is we're going to determine the work function for the unknown material, and I want to know what material is it. Okay. Anybody want to quickly shout out what the type of problem is, what principle is applied to this problem? Type it quickly in chat. It's the something effect. Uses frequency. Yep, it's the photoelectric effect. Okay. So this problem is a photoelectric effect problem. So let me switch back here. Let's go back to this. Okay. I'm going to erase this stuff here. Okay. So let me write down a couple of general things for the photoelectric effect first before we start attacking the question, just so we make sure we understand the concepts. So the photoelectric effect very brief summary of the photoelectric effect. You have a piece of metal. This takes, some material takes something like, could be anything ranging from, let's look at this table here, aluminum, cesium, gold, iron, lead, magnesium, a bunch of listed materials we have. So we have some material here, and what you're going to do is you're going to shine light onto it. Okay, so let's say that this represents the incident light that's shining into it. Okay, so the light hits the material. Now light has energy, and in this material there's a bunch of electrons. So electrons in material. So what will happen is the incident light will hit the material, and it tries to give energy to the electrons. Now, there's a couple of things that we notice in our observations. These are very important conceptually, and if you're doing like the final exam multiple choice, you'll probably see one of these as one of your questions if it asks about it. Okay. One observation that we notice is that the brightness of the light, or the intensity of it, does not affect whether or not the electrons eject from the material and begin to produce a current in the problem. So brightness or intensity of light does not affect if, okay, so it does not affect if the electrons are ejected. Okay. It does actually affect something, but if you're asking, do the electrons eject or not, it does not care. You can take a really dim light and a really bright light of some color, and it's not going to influence if it's a yes or a no. Okay? The other observation you make is that if light of a large enough frequency, okay, if we're talking about large frequencies, we're talking about smaller wavelengths. So smaller lambda wavelength. If light of a large enough frequency strikes electrons, they eject. Okay. So these are two good conceptual details to remember. Okay. The equations that follow with this are, so the main one that we're going to talk about is the energy equals HF minus, they call this different things depending on what textbook you go to or what professor you go to. In this class, it's indicated by W naught, I believe. Sometimes they also use a Greek letter phi in place of this. Okay. So defining everything in this equation, let's call this, let's call the diagram 1, this bullet point 2, 3, and 4. E is defined as the possible energy of electrons ejected. Okay. We'll be referring to the kinetic energy of the electrons. Okay. H is Planck's constant, F is frequency of the emitted light, W naught is the work function. Of material. Okay. Now, in this particular problem, so what we're going to be looking for, let's go back to here. So we're going to be looking for the work function of the unknown material, and we're going to determine what material is it. So simply we're going to solve for the work function in the equation, but also notice that, let's say if I ask you what material it is, then you can determine that because I give you all the materials and their work function. So when we solve for the work function, we're going to be able to line it up in the table and say, oh, it's lead, oh, it's copper or aluminum. So let's start by solving for the work function. Okay. All right, so let's go from here. So one last thing I'm going to add to this based off of the conceptual details. Oh, we need to switch back to here. Okay. So if you think of light as a wave, you're not really going to see so much why the electrons are doing this. But when you think of them as photons, and we know that photons have an associated energy with them, which is actually this part of the equation, H times F. If every photon has an associated energy, you think of it as one photon hitting a single electron, and the reason why the electrons will either eject or not is based on how much energy that single photon has, which is why it's determined by the frequency. So let's take this equation, and we're also given in this problem here that let's see, we're given that the electrons eject with a maximum speed of 1.00 times 10 to the 6 meters per second. So that value there is essentially telling us what amount of energy is going to be involved in the problem. So if I give you the velocity, you should be able to calculate the kinetic energy from that. Okay. So going back over here, let's look that up. So given the velocity is 10 to the 6th meters per second. 1.00, we're just going to drop that off. So this means that the kinetic energy, okay, so this you might have to dig back up. So kinetic energy is equal to 1/2 mv squared. And we can calculate what that kinetic energy is that we can use in this equation. So we have 1/2. Now because this is the velocity of the electrons that are being ejected, we're going to be using the mass of the electron, which is a known value. So the mass of an electron is 9.11 times 10 to the minus 31 kilograms times the speed that they're ejected with, 10 to the 6th meters per second, and then don't forget to square that. Let's call this 5. So having a small wavelength will make more electrons eject. So the answer to that question, yes, the smaller the wavelength, the higher the frequency. Either way, you can phrase it either way. And having a smaller wavelength means the photons have more energy, and that means they're going to at some point eject the electrons when they have enough energy from that smaller wavelength. So that's correct. And the other question is, so would it also change its energy? Yes. So if you're referring to the photon energy, yes, it changes the photon energy because the wavelength and the frequency go directly hand in hand with the energy of it. But it would also change the energy of the ejected electrons because you're giving the photons more energy, and more of that energy gets transferred into the kinetic energy of electrons as they produce a current in the problem. So, now, okay, so another question is, intensity affects the number of photons. So if you look at these statements here, I'm only referring to if the electrons eject or not. So if you want to talk about more electrons being ejected or more photons, you can turn up the brightness or the intensity of the light, so you can make it brighter, and that still will not change if they eject or not, but it will give more photons, and then it could produce more electrons that eject, given that they do eject already. Okay. Does that make sense? Are there any other questions on those ideas or any of the stuff I have written so far? Okay. All right. Okay, so we calculate the kinetic energy. Kinetic energy equals. So start with this. 10 to the 6th, square that, it's 10 to the 12th. So that times 1/2, 9.11 times 10 to the minus 31. And then 10 to the 12th. Okay, so the kinetic energy that we get out of this is 4.56 times 10 to the minus 19th. And now you're getting an energy, but you're using all the standard units. So you're using mass in kilograms, velocity in meters per second. You're going to get newtons, meters, and that's going to give you joules by default. Now that you have the kinetic energy, from here, you can use that in here for E for the energy of those electrons that they could possibly have, and we can solve this for the work function. So intensity will affect the amount of electrons, but also the wavelength. They both produce more. So if you have, well, okay, so not necessarily. So let's say that you have a photon and you give that photon more energy. You get a larger current out of it. Now, larger current could mean one of two things, is that either the movement of electrons are faster, or it means you have more electrons moving in unison together. So you could take a single photon, let's say, and send that photon to the material, and let's say you only eject one electron, okay? But if that photon has more energy, then that electron could, for instance, have more kinetic energy, and it'll register more current just simply because it's moving faster. You could then also get more current by shining a brighter light onto it, so you have more photons hitting it, you get more electrons ejecting, so that can also give you more current just simply because you have more electrons moving together. So smaller wavelength will produce more number of photons. No. So the smaller wavelength is going to change the amount of energy per photon. So when you use E equals HF equals hc over lambda, the energy of a photon, if you just increase the frequency or if you decrease the wavelength, it's just going to make the energy of a single photon bigger from that. So it's not going to give you more photons. So more photons is going to be, you make the light brighter, you make it more intense. You take something like sunlight, which is really bright, it means there's a lot of photons coming at you, as opposed to something really dim, which means there's not very many photons. Does that make it a little bit more clear? Are there any other questions? Okay, okay. So we need to solve for the work function. Okay, so what I'm going to do is I'm going to take this equation here and I'm going to solve it for the work function. So the work function, let's label this 6. I'm going to need to move the HF over. I could either do that, or actually I could swap places with the work function and the energy of the electrons. So I'm going to move the W naught over so it's positive, and I'm going to move the E over so it's negative. So I have that W naught, so solving for W naught. W naught equals HF minus E. Okay. So algebraically solve that. Now, rereading the question, because we need to plug in a frequency as well. So from the question, we already worked with the maximum speed of the electrons, but I did tell you something earlier on. So I said that it is found that when illuminated with indigo light, so I give you a wavelength of 450 nanometers, no electrons are detected. Okay. Notice this is an instance of having, okay, so indigo light in some problems, 450 nanometers, might be actually relatively energetic. And in some materials, that might be enough to eject electrons. In this case, you detect no electrons. So that's not quite enough energy per photon to eject it. However, when the metal is illuminated with ultraviolet light, okay, so we're going more energetic, wavelength is smaller now, it's 190 nanometers. This is now able to eject the electrons, and they eject with the given speed of 10 to the 6 meters per second. So in this problem, you want to use the wavelength that is associated with them ejecting, and specifically the speed that I told you that they eject at. So we're going to use the 190 nanometers. First thing we should probably do with this, though, is we should take it and change that to frequency. Okay? Because this equation does not have the wavelength in it. We could just change, we could either change the frequency to wavelength, or we can take the wavelength and just convert it to frequency. It doesn't really matter which way you go. So let me write over here that the frequency, I'm going to use a different color that's a little bit better. Let's use this red. So frequency equals C over lambda. Okay, so just use this equation here, C equals lambda F, and solve it for the frequency. Plug in the value of lambda. Okay, so when you're given that lambda equals 190 nanometers. Okay, this is what it took to eject the electrons with that speed. This means that the frequency is going to be speed of light, which is 3 times 10 to the 8th meters per second, divided by 190 times 10 to the minus 9th, because nano meters. And we're just going to calculate this frequency. So we have 190, 10 to the minus 9th on the bottom, and we have 3 times 10 to the 8th on top. So what we get for the frequency is 1.58 times 10 to the 15th. Now, if you just do the unit cancellation here, you lose the meters and you're left with 1/, seconds. Okay, this is valid here. You could leave it like that, it doesn't really matter. This is preferred to leave it like this if you want to show how the units cancel. Otherwise, 1/, seconds is the same as the unit hertz. All right, so now that we have the frequency that corresponds to our ultraviolet light with that given wavelength, let's plug everything in. I'm going to erase starting from the left side. Are there any questions up to this point on what I've done so far? And let's go from there. Okay. Looks like we're good. Okay. So let's erase from the left side. Okay. Let me label a couple more things. This was 7. Let's call this down here 8. Okay, so let's go back to this equation here. So work function equals Planck's constant, 6.626 times 10 to the minus 34th joules times seconds. I'm just going to erase a little bit more so I don't have to do anything funky with writing that. So that times the frequency, which is 1.58 times 10 to the 15th. I'll write as 1/, seconds to show that the seconds cancel, minus the energy that we're using. The energy that we were using, which I conveniently erased. If someone can quickly type that energy into chat, otherwise I'll just recalculate it real quick. Okay. Let's see. Times 10 to the minus something joules. Okay. 4.56. Times 10 to the minus 19th joules. Thank you. Okay. I hate when I do that. Okay. So let's calculate this out. Frequency times Planck's constant, 6.626, times 10 to the minus 34. Okay, so we have the value here, and we're going to subtract off the energy. 4.56 times 10 to the minus 19th. Okay, so the value that I get for this is 5.90 times 10 to the minus 19th. Okay, we get joules. Okay, notice that the first term, the seconds disappear, you're left with joules. Second term, also in joules, joules minus joules equals joules. Now, you could technically leave that as your answer if you were just simply asked what the work function was equal to. I never said that it needed to be in electron volts technically, but if you wanted to line that up with the value in electron volts, and then in this problem I ask you to determine the material, then we need to get it in electron volts and then line it up with what material it is. So we're going to do a conversion on this. Call this one. So for our conversion, we're going to take this value, 5.90 times 10 to the minus 19th joules. And we're going to reuse that conversion that we used in the last problem. So we have 1.602 times 10 to the minus 19th joules per 1 electron volt. So remember, it was just the charge of an electron that was the value for the conversion. Equals. Don't forget to put the bottom in the parenthesis again. So divided by 1.602, 10 to the minus 19th. Insert. Okay. The value I get here is 3.68 electron volts. And this is the work function for the material in electron volts. Now, if you go back to the table here, let's go back to the worksheet. When we look at this table, we're going to use the closest value to 3.68, which I designed to make it fit into the table. So you'll notice that that lines up with magnesium right there. Okay? So let's write down that that's magnesium. And then I have a question. Okay, so magnesium. Your question is, why did we solve for the kinetic energy on the previous board? So if you look at the work function that I had to solve for, okay, there is the energy term, E, that we need, and that's referring to the energy associated with the electrons that are ejected, the maximum kinetic energy that they can have. I gave you a velocity which would allow you to solve for that energy, and then you would use that energy to plug into there. So that's why I was using the kinetic energy on the previous board. Does that answer that question? And are there any other questions on what I have here? I'll label this 2. Do we have a part B to this? Yes, we do. So part B. Calculate the wavelength of light necessary to just barely begin ejecting electrons. Okay, so we need to find the wavelength of light, so we need to solve for a lambda somewhere. We already have some values of lambda, but we need to solve for a separate value of lambda. But the key words here are just barely beginning to eject electrons. In other words, when you think about the photoelectric effect conceptually, okay, so remember that you have to give the photons enough energy per photon, so E equals h times f. You have to give it enough energy through means of raising its frequency, or also meaning decreasing its wavelength. At some point, when you give them enough energy, the electrons will just barely begin popping off, okay? So in that case, you're going to use a value of 0 for the energy that they eject off with, because that's the absolute minimum amount of energy they could possibly have. Okay, if it has even 1 joule of energy, then it's not just barely; it's already beginning the process of ejecting off. So we use the value of 0 for the energy, and we resolve the problem. let me see. Okay. Could we also use work function equals frequency times Planck's constant? Yes. Okay. So let me go over here. Let me leave that stuff there. I think I can fit this down here. Okay. So this is part B. So you have a couple ways you could do this. There is a way that you could, I guess, just remember, which is to just use work function equals h times a frequency. But then you kind of had to remember that. But the way I see it intuitively done is if you know that they're just barely being ejected off. The minimum amount of energy that you start with is 0 before you start gaining energy at that point. So what you're going to do is, so just barely ejecting, okay? This is another way of saying basically solve for the cutoff condition or the cutoff wavelength, the cutoff frequency. So cutoff frequency or wavelength. Okay, so we're going to still use the same equation. E equals HF minus W naught. Okay. We already know the value for W naught now because it's magnesium. We already know it's going to be magnesium for the whole problem. Okay, that was the point of solving for the first part, is to find out what it was so that we can just know it's magnesium here on out. So we have the value of W naught now. What's going to change is we're going to use a different value for E because it's a different condition in the problem. It's condition just barely needed to eject the electrons. So what we're going to say is that where E equals 0, okay, I'm going to set E equal to 0 to satisfy the just barely condition, the cutoff frequency. Okay? So setting E equal to 0, what's going to happen is you're naturally going to find what you need to do this. You notice that if you were to solve this out, so you solve for W naught and put it on the other side, you'll find that W naught equals just H times F. You could use that as your starting point, but this would be basically the intermediate steps needed to get to that point. And this, in my head, makes a little bit more sense to reason it this way to be able to use that formula. But otherwise, to answer your question, yes, you could jump to that step. So E equals 0, so the velocity is 0. Yes, that's correct. Okay, so if the electrons have no energy, then you're giving them basically a 0 velocity, essentially. So from here, all you're going to do is you're going to solve for the frequency from here. Frequency equals W naught divided by H, Planck's constant. Okay. Let me label this. So this is, let's call this 3, 4, and let's call this 5. Okay. So what we're going to do is we're just going to plug the work function into here and then divide it by Planck's constant. But the thing is that you have to be careful about is, again, pay attention to your units. Planck's constant is most likely going to be in joules and seconds, but then your work function a lot of times will be written in electron volts that you have to be really careful about because electron volts are not going to cancel evenly with joules. So what we need to do is we need to use the joule value of the work function that we solved and plug it into here, if that makes sense. So, in other words, 5.90 times 10 to the minus 19th joules divided by Planck's constant in joules, 6.626 times 10 to the minus 34 joule seconds. Okay. So, plug that in, calculate the frequency. So this equals 5.90 times 10 to the minus 19th, and then over that whole number, 6.626, 10 to the minus 34. The frequency that we get is 8.90 times 10 to the 14th. Notice the unit cancellation leaves you with only 1 over seconds, which is the same thing as hertz. Okay, so that is indeed a frequency. Okay. But this is not quite the answer that you wanted, even though it is correct. We didn't want the frequency, we wanted the wavelength of this. So all we're going to do from here is just put this back into a wavelength. So let's call this 6. So wavelength equals C over F. So again, use the same equation we've been using to change back between frequency and wavelength, and just solve for the wavelength now. So this equals 3 times 10 to the 8th meters per second divided by the frequency, which we calculate to be 8.90 times 10 to the 14th, 1 over seconds, or hertz. Okay. So the cutoff wavelength, that wavelength of light that's needed to just barely begin popping off electrons, okay, that's going to be equal to that number at bottom, and then that number on top for the speed of light, 3 times 10 to the 8th, okay, and scientific notation. So the wavelength is 3.37 times 10 to the minus 7th meters. Notice again the seconds cancel out properly, so you get meters. Or, in other words, lambda equals 337 nanometers. Okay. So that is the answer to your part B, is this wavelength here. Okay. Oh, hi. Hello. Okay. So notice that the answer we got, okay, so how do you know this answer is going to make sense in this problem? How can you be assured that this is reasonable? So if you go back to the problem here, okay, so notice the context of the problem is that we illuminated the material with indigo light. Whoops, don't want to drag that. Okay. We illuminated it with indigo light, so it's 450 nanometers, okay? But the result was that no electrons were detected, okay? Now, what we do is we continue to decrease the wavelength from 450. So we decrease, it's now 400, it's now 300 something, it keeps going down. So we're giving the photons more energy. At some point, they will eject. According to our problem, our answer is 337 nanometers, which is smaller than 450. So now they begin to eject, and if you continue after 337 nanometers, down towards like 190, which is even smaller, they start picking up even more energy. So our answer makes sense because it flows with the context of as you decrease that wavelength, you'll go from not ejecting the electrons down to smaller wavelength where you will begin ejecting electrons, and then after that point, you're just giving them more and more and more energy. So they move faster and faster. Does that make sense? Are there any questions on anything I have written up here? Anything to do with the photoelectric effect before I move on to the next problem? Okay, thumbs up. Anyone else before we move on? Okay. Let me take a look at the next problem, and I'll pay attention if there's any other questions. We got a question. Why did we solve for kinetic energy on the previous board? So to reiterate that, oh, you copy that. Okay. To reiterate that briefly, the context of the problem was that we were given a velocity of the electrons, and we were looking for the energy from that so that we can plug it into the equation. So the equation was solving for the work function, W naught, and we were missing the energy, which was the kinetic energy of the electrons. So we needed the kinetic energy first before we could solve for that. So we used the velocity to get the kinetic energy to then solve for the work function of the material. Let's take a look at that next question. If there's any other questions, feel free to pop them in. Okay, so next one. Okay, so I saw that one of the questions was a double slit experiment on her version of the practice test. So on my version, I decided to do a single slit. Just to cover all the bases. I'm not sure what she intends to do exactly on the final, if she's going to follow that practice exam for like topic for topic, or if they're going to be similar topics. So I decided to do a single slit for this one. Let me know if you have any more details on what she decided to do for the final, or if we can just keep on going with this. So, so this one, number 3. We have monochromatic violet light with a wavelength that's given. So the wavelength is 450 nanometers. Shines onto a single slit. So you can see here, there's our single slit, and here's the incident light to it. Has a width given of 25 micrometers. And what we notice is a light pattern that's cast onto the viewing screen, which is 75 centimeters away from the slit. So the distance between the slit opening and directly to the viewing screen over to here is 75 centimeters. We're going to find first what is the width of the entire central bright spot. So width of the entire central bright spot. So let's briefly discuss this conceptually, what happens to kind of get what we're being asked here. So I'm going to erase this board here. Let's see here. Okay, looks like we're okay. Now, when you do the single slit problems and the double slit problems, you're going to find that it's done in a very similar way to each other. So this is another reason why you should probably think about looking at the single slit problems too, in addition to your double slit problems. So this is single slit diffraction. Okay. So we have this setup here where we have our single slit and we have a viewing screen. Okay. We have some distance separating the two. So the distance that we're going to call between the single slit and the viewing screen, let's just call that L. Let's call the width of the slit W. If she uses a different variable in her notation, let me know. Otherwise, a lot of textbooks do W for the width of the slit. So the distance across this gap here is going to be W. Okay. And what we're going to see on this viewing screen is not a single beam of light. What's going to happen is when this slit width is small enough and it starts getting smaller and smaller and comparable to the wavelength of light. So the wavelength of light is probably somewhere around like a micrometer. And the slit width is a handful of micrometers. So whenever that happens, we're going to notice diffraction. So what we'll see is not a single bright spot in the center where the slit is, but you'll see a bright spot, dark spot, bright spot, dark spot, bright spot, and alternating out and getting continually dimmer as you go out. But you'll have an alternating pattern of bright and dark and bright and dark. Also, this is a rough drawing. What will happen is it will be very bright in the center. It'll get dimmer and dimmer and dimmer as you go out until it becomes a dark spot. So it gradually transitions into being dark, and then it gradually transitions into being bright again, and then so on and so on. Okay. Let's call the distance, or let's say this distance is L, so I'm going to draw this line down the center. Let's say that if I want to talk about a particular spot on the viewing screen, so I want to talk about, oh, this first dark spot, or this first bright spot from the center. What will happen is you'll end up panning out some angle from the center to the point of interest that you're looking at. So let's say we pick this point of interest. There's some angle in here. Let's call that angle Greek letter theta. And for single slit diffraction, we have this equation, W sine theta equals m times lambda. Okay. Let's call the diagram 1, and let's call the equation 2. So this equation, where we have that W is the slit width, theta is the viewing angle to whichever point of interest you want to talk about on the viewing screen. M is what's called the order number. So M is defined as the order number. It's referring to how many spots away from the center you are, essentially. There's more to it than that, but we're going to start with that. And then lambda is the wavelength. Okay. So in this problem, what we're looking for in particular, we're looking for the width of the entire central bright spot. Okay. Question, W equals sine theta. W sine theta equals m lambda for dark. Yes. Let me write that in a second. Let me clarify that. So this equation here that I wrote out, okay, this is for dark fringes or spots. Okay. And what you're going to do with this equation is you're going to count the number of dark spots away from the center that you want to use. So for instance, if I want to use the first dark spot away from the center, I use m equals 1. If I want to use the second dark spot, it's m equals 2. So again, the m value is just counting how many dark spots away from the center there are. Okay. So there you go. Do not use this equation for the bright fringes. It's a little bit more complicated with bright fringes, so we're gonna use this equation for the dark fringes to solve this. Now, the problem you might realize with using this equation is, okay, so if I look at part A again, okay, so in part A, I asked you not for a dark fringe. I asked you for a bright spot in the center specifically. The thing is that you have to be a little bit, you have to think a little bit outside the box on this one, because the center bright spot, if it had any value you could associate with it for an m value, which you would not do, by the way, if anything, it would be m equals 0, but we're not doing that. But we can't solve that if it was 0. So what you have to do is realize that the width of the central bright spot, so how wide is that spot on the screen? So if you took like a ruler and measured it, the thing is that you would take your ruler and you would start from where the dark spot is and then measure all the way across it to the other side to the other dark spot symmetrically. So you go from the m equals 1 dark spot on one side to the exact symmetrical point to the other m equals 1 dark spot. So you're really going to use m equals 1, and you're going to still be talking about a dark spot. So the trick to this problem, also a typo by the way, it's not 10 degrees here, leave that as a question mark. The thing with this problem is that you must solve for where the first dark fringe is, because finding the location of the first dark fringe is what determines where the end of the central bright fringes. So we're going to solve for the angle that corresponds to the dark fringe. Let me clarify a couple more things here. So we have this equation here. So this is going to allow us to solve for an angle that corresponds to where that dark fringe is. So for instance, the angle theta would be equal to 0 if you were talking about the direct center. But that angle continues to increase in size as you go further and further and further out. So we want to solve for what angle of theta corresponds to that first dark fringe, and what that will allow us to do from there is then find a distance that corresponds to that angle. So that's why we're looking for theta. So I'm going to take this equation here, and I'm going to first solve it for theta. So the first thing is I'm going to divide off by w to the other side. So we have sine theta equals m lambda over w. Okay. The sine of theta is isolated, so we're going to just take the inverse sine of both sides. Okay. So this implies theta equals the sine inverse of all of the stuff on the right side. So m lambda over w. Okay. We've solved for theta, so now we just plug in each of the values. Okay, so let me write real quick again conceptually. So this is, let's call this 3, let's call this 4, and let's call this 5. So again, conceptually, the end of a bright fringe is where the dark fringe is. Okay. So for this, again, we're going to plug in m equals 1 for the first dark fringe because that's the dark fringe where it ends the central bright fringe. Okay. So for center bright fringe, use m equals 1 dark fringe. Okay. So now we're going to plug in to the equation and just calculate this angle. So theta equals sine inverse of m equals 1. Lambda is given in the problem. Okay, so lambda is going to be 450 nanometers. Okay. So 450 times 10 to the minus 9th meters divided by the width of the slit, which is also given. It is 25 micrometers, so 25 times 10 to the minus 6th meters. Let's calculate this out. So 25 10 to the minus 6th, the bottom, and then on the top is going to be 450 10 to the minus 9th. Okay, and then we're going to take the sine inverse of this whole thing. So the sine inverse of the answer is, I get a value of 1.03 degrees for this when you're using degree mode. Okay. So theta equals 1.03 degrees. Okay. This is the angular position of the first dark spot. Okay. So that's what we got so far. But then let's go back to what we were ultimately trying to get out of this. Okay. So we wanted how wide the center bright spot is in distance. So here again on the diagram, we need the distance between, let's use green. We need the distance between this dark spot here and that dark spot there. Okay. The distance between those two dark spots symmetrically about that center bright fringe is that distance we need. Okay. Let's call this distance delta y. Okay. Whatever you want to call it that doesn't conflict with any other variables, let's just call it delta y. I called it delta y also simply because the variable y is often used to express the distance from the center of the viewing screen where m equals 0 all the way out to whatever point you're questioning. So the value of y again is the distance from the center. So delta y is actually going to be related to what the value of y is. I am going to erase part of this board, starting from the left side down here. Does anybody else need anything off this board, or are there any questions on what I've written so far? Also, feel free to give a thumbs up or a short little got it, just to let me know that everything's all good in the hood. Okay, looks like we're good. Okay, let me start erasing from the bottom left side. Okay, so good. So I'm going to try to retain the diagram because we already have the equation, so I'm going to start erasing from 2 down. Okay, let me label some of these. So 5, let's call this 6, and let's call the answer 7. Okay. So, I'm going to draw a separate diagram to show you what you're going to do to get this distance between here and here. It has to do with this angle theta. Actually, in fact, I can just use this in the diagram. If it's big enough, then it should be good. If it's too small, let me know. But what we're going to do is we're going to use this viewing angle here, theta, and we're making a triangle out of this distance here, diagonally, the distance L from the slit to the viewing screen, and then we're going to use this side length here. Okay, so let's call this distance in here along the wall, the viewing screen. This small little distance in that triangle is going to be y. Okay. I'll actually copy the triangle down off the diagram. So the triangle I'm using is this one right here. Theta, L, and Y. Okay, and it is a right triangle. Technically, you could just say, okay, there's a formula for this, but this is where the formula comes from, is this right triangle. Given that you want to find the value of Y, and you know what L is, and you know what theta is, you can solve that. Because with respect to this angle, Y would be the opposite side, L will be the adjacent side, so opposite and adjacent are connected by a trig function. It's tangent. So the tangent of that angle theta is equal to opposite, which is y, divided by adjacent, which is L. Okay? This is where you get this equation from. Now, we want to solve for y, so y equals L tangent theta. Let's call this, so that's 1, let's call this 2, 3, and 4. Okay. We've solved for y, and we're just going to plug in because we have the values. So L, you technically have it in centimeters. I gave it as 75 centimeters. You could leave it in centimeters if you really wanted to. Doesn't hurt to change it to meters either. So let's just say we use meters. So 0.75 meters is 75 centimeters. Tangent of, so the angle that we're going to use is the angle that we just solved for the location of the first dark fringe. So we're going to say it's 1.03 degrees. We're going to do tangent of that and times that. Tangent 1.03 times 0.75 the value of y that we get is going to be 0.014, let's say. Let me write 35 for now, so 0.0135 meters. You could change this over to some unit prefix variant of this. I would say if you want to change it to moving it 2 or 3 decimal places, you can make this 1.35 centimeters, or you can make it 13.5 millimeters. So either or. So this is, let's just say it's 13.5 millimeters. Okay. Now, we have the value for y that corresponds to the distance along the viewing screen that the dark fringe is away from the center. Now realize that at this point we've pretty much solved the problem other than doing one minor detail, because the distance y from the center to this first dark fringe, you just have to mirror on the other side, which is exactly the same distance, and the total distance is actually just 2 times y, which is what we're calling delta y. So over here, let's write that delta y, the distance between the 2 dark fringes, which is going to encompass the entire central bright spot, is actually just 2 times the value of y, and that's just 2 times 13.5 millimeters. So therefore, the value of delta y is 27 millimeters. Okay. And that is the width of the center bright spot. Let's label this, let's label this down here 5. Let's call this 6 and then 7. Okay. All right, so that solves the part A of the problem. If there's any questions, let me know on this. Give me a thumbs up, let me know. And then we'll do part B. So let's take a look at part B. Okay, so part B, we're going to calculate the angle subtended from the slit to the second dark fringe on the viewing screen. Okay. This is basically the same as the first question, partially, because I'm asking you to just solve for the angle to the second dark fringe instead of the first one. So all you have to do is solve for theta and do it for the second dark fringe. That's it. Okay. Most of the work was in the first part. Okay. I'm going to erase starting from the left. Actually, I can probably squeeze in this space right here. I'm going to erase this corner here. Okay, so for part B, okay, angle to second dark fringe. So there are 2 equations we have so far that have the angle theta in it. So we have the one we just used, which is tangent theta, but this one may not be so good because we would need to know what the value of y is for that particular dark fringe. The value of y for the first dark fringe was 13.5 millimeters, but we're not talking about the first one anymore. So the value of y is going to increase up to the second one. So we don't know what y is, but we do have the other equation which says that w sine theta equals m lambda for the dark fringes in the single slit. So we're going to repeat by solving for theta again. Theta equals sine inverse of m lambda over w. So again, move lambda over and then take the sine inverse of it. Equals sine inverse of m equals 2 for the second dark fringe. Same wavelength given the problem, which was 450, I believe, times 10 to the minus 9th meters, divided by the width of the slit, and the width was also given, which was 25 micrometers, so 25 times 10 to the minus 6th meters. Okay. This angle equals, so plug in, bottom is 25, 10 to the minus 6th, and then top is 2 times 450, 10 to the minus 9th. And then we're going to take the sine inverse of that. Okay, so the angle to the second dark fringe is 2.06 degrees. Equals 1. Okay. So to emphasize this over here, remember that since I asked you for how wide the center bright spot was, so the center bright spot is here. Because you want how wide it is, remember the crucial fact is that where the bright spot ends is where the dark spot is. So you use m equals 1 for the dark spot to say that's where the bright spot ends. And because that's going to be the same on both sides, you use m equals 1 and m equals 1. They're both the same value for theta and y, so it was 13.5 millimeters away from the center for that first dark spot, and then you mirror it on the other side to get distance from dark spot to dark spot to get the entire center bright spot. Does that make sense? Okay, awesome. All right. Are there any other questions on part B of this problem, anything I have on the board, or anything from part A, anything with single slit diffraction before we move on to the next problem? Give me a thumbs up if everything is good. Everything is great. Awesome. Great as in it's really great, or great as in I'm slowly dying inside because finals? Let's see here. Let's go to the next one. Both. It's truly great. Okay. All right. So next one. Let's see here. Now this one is a mirror one I did. Again, I don't know what she decided to do for the problems precisely. If she's going to go off of her practice test more or just use similar concepts. But I'm doing a mirror one in this case because it's analogous to the lens one on the other practice test. So again, let me know if we should focus on other things based off of what she said. Okay. So for this one, there's a few things we're going to do in it, and this is something you could do basically for a mirror or for a lens, regardless of the problem, because you basically have the same equation, which is 1 over f equals 1 over do plus 1 over di. You just call one the mirror equation, you call one the lens equation, but they are basically the same thing. there's subtle differences, such as the mirrors will use a radius of curvature, and you have to do half the radius of curvature to get the focal length. That's a subtle detail about that. And then you may have to do ray traces for them, possibly. So we'll just run through this, but notice that you could do something very similar for a lens problem. So for this one, we have a 10 centimeter tall object. It's held at a distance of 35 centimeters away from a spherical concave mirror. So here's the object that I've drawn in. Point C here labels the center of curvature of the mirror. So if you were to imagine that if this is the mirror here, then the mirror basically follows a sphere, or if you cut it so you look at the basic shape, it's a circle. So a circle would essentially wrap around this point C where it's the center. Okay, so the radius of curvature will go from this point C all the way to where the mirror is. Okay. It's a concave mirror. Okay, so if it's a concave mirror, what that means is, remember that if light will shine from left to right, then what will happen is if light shines from left to right, then concave will mean that it bends away from the light. So notice that the shape of the mirror bends to the right away from the light. If it's convex, it bends towards the light the other way. Radius is given. It's 15 centimeters. And we're going to find a few things in here. So first thing we're going to do is we're going to do a ray trace. I'm going to go over quickly how to do a ray trace with 2 or 3 rays, the ones that I use at least, that make life relatively easy. So let's draw this out real quick. Okay. We're sitting about 10 o'clock, so things are looking good. So let me draw this in on the board here. Now, what I recommend doing is, if you have to do drawings like this, or drawings in general, it's always better to draw them a little bit bigger than smaller, because the smaller you draw it, the harder it is to interpret what's going on, and it makes it harder on yourself. So for me, since I have all the space in the world, I'm just going to draw on the whole whiteboard. So this line represents the center axis that divides the diagram in half, top and bottom. I'm going to have the center of curvature here, call this point C. And I'm going to have my mirror right here. Okay. So what I did here for my drawing is I made a semicircle here just to draw in the mirror nicely. So I'm going to draw my mirror like this. Okay, here we go. And I'm going to erase the rest of the details. Okay, so here's our mirror. This is concave, and our object is placed 35 centimeters away from the mirror. So if you're thinking about the distances in the problem, the radius of curvature is 15 centimeters given. That's the distance from C to the mirror, like this. Now, if you were to kind of put this distance on the other side, 15 over here, that makes a total of 30, and the object is a little bit further away than that, it's 35. So let's call this object. Okay. And let's do a ray trace. So what I usually do for these ray traces is I pick out 3 rays that are easy to do. Okay. The first ray I'm going to do is what's called the parallel ray. Starts from the top of the object at this point. Most rays will start from the top of the object. And if it doesn't start from the top of the object, the condition is that it should go through the top of the object. So parallel ray will start at the top of the object, and it's going to go parallel to this center axis, that's the horizontal line. So it's just going to go parallel to that line, like that. Okay? So let's draw that. This is a parallel ray. This ray will hit the mirror. Now, anytime light hits a surface, it's going to partially reflect off of it, so it follows the law of reflection. You could do that here, but the idea of having these special rays that I'm going to draw is that if you remember that these rays do certain things, you don't have to do anything fancy with the rays, like draw certain angles or anything. So the one thing you need for the parallel ray, though, is to label where the focal point is. So whenever you have a spherical mirror, so in this case the concave mirror, you would realize the mirror is here and the center of curvature is here. So the distance here is 15 centimeters. The focal length is half of that distance. So remember that the focal length, the absolute value of the focal length is the radius divided by 2. So I can take these 2 points between the mirror and the center of curvature, focal point's right in the middle. Okay, so that point is, let's call it F. Okay. Now, we need to know where the focal point is in the drawing because the parallel ray will hit the mirror and it's going to exit out through the focal point. Okay. So it's going to go off the mirror and it's going to bounce back like Big Sean. Bounce back. And then it goes through the focal point like that. Okay. Now, so we have the parallel ray drawn. I'll actually extend it a little bit more just in case this goes out further. I'm going to do 2 other rays. So the next ray I'm going to do is take from the top of the object, and it's going to go to what's called the midpoint or the vertex of the mirror. If you want to label this point in the diagram, you can. Basically, the middle of the mirror where it meets the axis, let's call that point, either M for midpoint or V for vertex, either one. Let's call it M. The next ray is called the midpoint ray. So what happens is it goes from the top of the object, and it's aimed to the midpoint of the mirror. And this one's really easy because whatever you do above this line, this axis here, you just flip it below. It's exactly the same below. So we go to the midpoint, like that, more or less. And then just take this and mirror it below. Like that. Okay. Notice how when you do this ray, there is an angle from the axis to that ray, and there's an angle from that axis to the ray below. That angle is actually the same angle. Okay? That's how you'll know you've mirrored it over. Okay. Now, the reason why we need to do 3 rays in the ray trace, at least for mirrors, is because the image is going to form where the rays meet. But the problem with that idea is that in this diagram, there's at least 2 crossing points where the rays meet. So the real question is, well, which one is it? How you know for sure is by doing a 3rd ray. And where all rays cross is where the image forms. Let's do a different color. Let's use this red. And let's label this the midpoint ray. Okay. So last ray, again, top of object. The condition here is that the ray needs to go from the top of the object through the focal point first and to the mirror. So top of the object, through the focal point, continuing through, hits the mirror. Now, after it hits the mirror, it's going to do exactly the reverse of what the parallel ray does. It's essentially just a parallel ray in reverse. Notice that the parallel ray goes in parallel and out through the focal point. the focal ray, as we'll call it, goes through the focal point and it goes out parallel. So from here, it's going to go out like this, out parallel. Now notice that despite the crossing points in the diagram being numerous, there's only one place where all three rays cross, and that's where the image forms. So the image goes right here at this point. So you always draw from the axis down to the crossing point or up to a crossing point. So this right here is our image. Okay. Now, once we have the image, now in the ray trace, you could already figure out what kind of image it is based on the diagram. So there are a few descriptions we're going to be using. One of the descriptions that we're going to be using is referring to the position of the image. So image descriptions. Okay. So when you're referring to, let's call this actually the type of image. Okay. Which the type of image has to do with where the image is located, so the positioning of the image. So it has to do with positioning, of image. Okay. The types of image are going to either be real or virtual. So we have type 1 is real, and type 2 is virtual. Pinocchio wants to be type 1. Now, type of image, we can also talk about which way is it oriented. So is it right side up or is it upside down? So the terms we're going to use for the orientation of the image. Okay. Let's say right side up is called upright. There are synonyms for that word. It doesn't really matter what you call it as long as it means upright. And the other type is inverted or upside down. So these two will describe which way it's oriented. And the last image description we need is the size of it. So image size we can either say it's grown bigger, so we can say it's bigger or enlarged. We could say it's the same size. It's rare it's the same size, but you technically can't say it's the same size. Or you can also say it's gotten smaller, or other words that are used are either minified or reduced is the most common one. So reduced. Okay. Okay, so these are all the possible image descriptions that we can use, and then just again you could use same size if that's the case. So when you look at this ray diagram, look at the image. So let's start with the type of image. The thing is that how you know if it's real or virtual, you can do it in one of two ways. The way I like to go with is if you look at what all the rays are doing, okay? These rays of light are actually here, okay? So they're drawn as solid lines. The rays actually do cross here, okay? So that actually just makes the image real by default, okay? So at this point here, all light rays are physically present. What I mean by physically present is that you notice that these rays would hit the mirror and they would bounce back. Think of it as if you had a laser beam, the laser would hit the mirror and the laser would bounce off the mirror. So the light would actually go through this point. In some problems with different positions of objects, you may not always produce a real image. So what will happen is, in some cases, the rays may not always end up crossing somewhere. You'll end up having to do something like tracing the rays back, which is another problem which we could do on our next live stream. But the ray would be it would end up being traced back behind the mirror, for instance. And the thing is, behind the mirror, it's dark. There's no light actually there. If you have to trace rays back to a place where they're not actually there, it's just where they appear to come from, that's going to make something virtual. Or option 2 is you can just say, oh, the image is in front of the mirror on the same side of the object. It's real. Okay. The virtual image will end up behind the mirror. So, or image is on same side as object. So both of these are to say that it's a real image. Now, the other descriptions are relatively straightforward. This image is upside down. That means it's inverted. Okay. Just by looking at the diagram. So, image is upside down. This implies inverted. And the last description, now you could attempt to eyeball it, but how you know for sure if the image got bigger or smaller other than just eyeballing it off of a diagram that's somewhat questionable, if it's accurate or not, what you do is, in this case, you can use the rays to determine if it got smaller or bigger. So I want you to notice, for instance, that if you look at this green line where the midpoint ray is, from here to the mirror, and then back like this. So this midpoint ray. The thing is that it's symmetrical about the center line. So whatever it looks like on the top is exactly what it is, just flipped below the axis. The thing is that because the image is closer to the mirror than the object, the image hits the green line sooner than the object hits the green line over here. So because of that, the image actually ends up being smaller. So if you can't quite eyeball it, then you can use the ray geometry to determine, did it get bigger or did it get smaller? By using things like triangles and saying similar triangles, one's bigger, one's smaller. So image size, so image is reduced. All right. This gives us all the image descriptions: real, inverted, and reduced. Now, if you're doing a ray trace and you're trying to get image descriptions, this can be one way of getting the descriptions. The other way of getting the image descriptions is by actually just calculating it. So you have at least 2 ways you can do this. And the other thing is, if you do both, the answers should agree with each other. So if you do the math, you should still get the same answers. So we'll do that too. Are there any questions on doing this ray trace for mirrors before I erase it and move on to doing the rest of the problem? Let me know, give me a thumbs up, and then we'll go from there. I'll switch back in a second. Let's look at the rest of the question. Okay. So for the rest of this, we did the ray trace. Okay. It seems like it's long based off of what we did, and it's worth not as much points, in my opinion. But it's because it takes a little bit more time to explain it, so it's going to take longer to do that. But when you do these, when you learn how to do the rays, you should be able to do ray traces in 30 to 60 seconds. It's relatively quick if you know what you're doing with them. We're going to calculate the image position. Okay, so we're going to need an equation to find where the image position is. Let's take some of the given pieces of information. So we know that the object's height is 10 centimeters, so 10 centimeter tall object. It's held 35 centimeters away from the mirror. That's the object distance. And the radius is 15. Radius of curvature is 15. Okay. Sometimes if they give you the diameter of curvature, that just means you need to cut it in half to get the radius of curvature. So let's go back over to here. Looks like we're good. So I'm going to erase this. So remember the image description we're looking for here to make sure that everything's supposed to work out. The answer should agree. Real, inverted, and reduced. So let's see if we get that with the math. Okay. So, part B. Find image position. Okay, so we're going to need a couple of equations. First one is going to be the one that gives us what we want. So we need the image position. So the image position is going to be given by the variable di. In some textbooks, they like to use different variables. So most common you'll see is di for image position and do for object position. In some textbooks or some professors, they'll use p and q for object and image. And there's other variations, but it's more or less the same thing. But let's write out the equation and I'll define what everything is. So 1 over f equals 1 over do plus 1 over di. Okay? Regardless of what you use for your notation, p or q, do, di, the equation is going to look the same, and this is what everything is. So I like do and di because it's intuitive that it's object distance and image distance. Okay. And f is the focal length. By the way, if you question what the 3-line symbol means, it's like an equal sign. It just means defined as. Okay. All right. Okay. Let's label these. So let's call this equation 1. Let's call the definitions 2. Okay. So I need to start by solving for di because that's the image distance and that's what I want. So I'm going to start by using this equation and I'm going to solve for di by moving the 1 over do term over to the other side by subtracting it. So what we get is 1 over f minus 1 over do equals 1 over f. Okay. I'm sorry, 1 over di, sorry. So you have 1 over di by itself. So now all you would need to do at this point is flip both sides to get the answer. If you choose to start plugging things in now, you don't want to forget to flip this. Okay, so what I'll do is I'll flip it now so we don't forget to flip it. So if you flip both sides, di equals 1 over all the other stuff. 1 divided by 1 over f minus 1 over do. So this will solve for di. Now that would require that you need to know the object distance. That's given in the problem. It was 35 centimeters from the mirror. The focal length was not given in the problem, but we can get that really easy with a simple equation from the mirror. The equation that relates the focal length to something we know is, since we know the radius, it's going to be the focal length equals half of the radius. Now, there is a little bit of a twist to this equation, is that the focal length is precisely equal to plus or minus radius over 2. Plus and minus is a sign convention which has to do with what kind of mirror is it. So, a long story short, use plus if the mirror is concave, and minus if it's a convex mirror. Okay, so this only applies for mirrors because for the lenses, when you do lenses, when we talk about convex and concave lenses, it's actually the other way around. So this plus minus is only for mirrors. So be careful with that. Okay? There is a better way to do this, but it will take a little bit more time to explain it, so I'm going to just cut to this. We can go through detail a separate time, but use this for mirrors. So because we have a concave mirror in our problem, we're going to choose the plus sign. Okay? We're going to use positive r over 2. So the focal length for our concave mirror equals positive radius, which is 15 centimeters, over 2. Okay? That's the only thing with a unit, so we're just going to get centimeters out of this. So we get positive 7.5 centimeters for our focal length for the mirror. Now that we have the focal length, we can plug that into the equation for the focal length. We can also plug in for DO, so we can now calculate the image distance. So DI, the image position or distance, is 1 over a bunch of stuff. That includes 1 over the focal length of 7.5 centimeters. If you wonder why I'm not changing it to meters, remember the only thing that needs to be true is that the units are consistent with each other. They work with each other. If you put this in centimeters, the only other things you're using for these values are other distances. So the only thing that needs to be true is they all have the same unit. So 1 over 7.5 centimeters, it is positive in this case as opposed to using a minus sign for the other mirror, minus 1 over the object distance. It was given in the problem. It was 15 centimeters. Okay. We're just going to calculate all of this stuff. If I were you, I would recommend doing the bottom first and then doing 1 over the bottom just to avoid any calculator mistakes that are inevitably going to happen. So we have 1 over 7.5 minus 1 over 15. Get the entire bottom. Then once you get the entire bottom, then flip it. So 1 over the bottom. And the answer we get for DI is going to be positive 15 centimeters. Let me label a couple more of these. So this was, let's call this 4, let's call this 5, let's call this 6, 7, and 8. Okay. Are there any questions on any of this? I think I see a couple of things. So for the lens, the focal length would be, it's negative focal length for concave and positive for convex. That is correct for the lenses. So for the lenses, again, it's the opposite. If you're doing a double double concave lens, it's going to be a minus sign. If you're doing a double convex lens, it's going to be a plus sign. Okay. So the shape of it, convex plus and concave minus for the focal length. Other question is, how is it related to far-sighted or near-sighted problems? So how is it related to? If you're talking about the focal length in relation to those problems, the focal length is going to be a property of the lens or the mirror. So regardless of the lens or the mirror, it's always going to be the same kind of focal length. So these are always going to be true for whatever kind of mirror, and the same is going to hold for lenses. was there anything, was that what you were asking, or was there anything else specific with the type of problem that we're mentioning for far-sighted and nearsighted that has to do with this? It's problem for, yeah, on the practice final, it's problem 4 on there. Are you talking about like how is it related in terms of like what we're doing here and how we're going to apply that to the other kind of problem, or are you asking something slightly different? Because this problem is a completely different problem than you use the same ideas in this problem, so you use the same equations, but I would say it's a different kind of problem. So you're still going to be referring to the same equation. You're still going to be saying, oh, for this lens it's positive, this lens it's negative focal length. But the nearsighted and farsighted problems are a little bit more beyond that, though. So I would say separate this problem from that problem of that type, but carry away the same ideas of what equations to use and the properties of your lenses and your mirrors. And then we could always, now when we do our next live stream, possibly, I'm looking at doing Sunday night. So go to my website for all the information you need on these live streams, but currently it's looking like Sunday night from 9 p.m. till midnight is what more people wanted. So we're all broke college students on caffeine staying up late. So we'll probably go over one of those on Sunday in case you want to do those. And I think a lot of us are probably in the same boat with that kind of problem with farsighted and nearsighted. So we'll definitely make sure at some point, most likely on Sunday, to be able to do one of those problems out. Are there any other questions? Thumbs up, thumbs down on this? We'll move on to the next part. Awesome. All right, so part C of this. So in part C, we're looking to calculate the height of the image. Okay. Now, we've actually already done most of the work for the problem, especially in terms of explaining how it works. From here on out, they're very simple. Once you get things like the image position where it is, you do the ray trace, that's most of the work for the problem. Now, to do the height of the image, you need another equation which talks about the height of it. There is one equation that does that. So let's write this out. Switch back. Okay. So I'm going to erase the left side of this. Let's see, make sure we're good. Ready for the next part, part C. Okay. So let's erase this side. Okay. So part C. Okay. Find the height of the image. And again, you can use anything you want, but normally they use h as the variable, maybe y, but hi for image height and ho for object height. The equation that we're going to need to relate some of these things together, especially because in my problem I gave you the object height, ho, how you're going to relate it to the image height, hi, is by using the magnification. So the magnification, okay, we're going to call the magnification m. Okay? And m has a definition. It's very, very simple. How big is the final thing compared to what the initial thing was? So how big is the image compared to how big is the object? So you would simply do image height divided by object height. That's what magnification does. So for example, if I calculated the magnification value to be 2, it means it got 2 times bigger. That's it. If it's a half, it's half as big. This is the definition of magnification, but it's also equal to something else if you have more information about the following. It's also equal to negative di over do, the image distance divided by the object distance. So this magnification formula collectively allows us to solve for one of these things. Because I was asking you for the image height, we're going to focus on that. But notice that if you look at this equation here, I gave you the object height. It was 10 centimeters, I believe. And we know what the object distance is. It was given. I told you it was 15 centimeters. And the image distance is what we already calculated. So technically, what you can do, let's call this 1. So what you can do is take this part of the equation right here, okay, and just equate them to each other. Just ignore using m because we don't need to find m to use these 2 parts here because they're both what m equals. Equate them to each other and solve for hi. So what we need to do is move ho over to the other side. So the image height hi equals negative di over do, all that times ho. Okay. So for each of these, we have them. Let's just plug them in. So negative, okay, image distance is positive 15 centimeters. Again, we can use centimeters because notice they're all distances and they're all in centimeters, so they're going to cancel out properly. Divided by object distance, it was given to be 35 centimeters, and the object height was 10 centimeters. Okay. So if you kind of look at this, but without calculating it, notice that if you just cover up the object height, which is 10 centimeters here, this part right here just tells you the magnification of the image. So if you were to just eyeball this, this is about 50%. 15 over 35 is a little bit less than 0.5. What that says is the magnification is about 50% or less, so it gets smaller. Okay? You're going to take that and multiply it by 10 centimeters to get the actual image height. So we should get something around like 4 point something, which is a little bit less than half of 10. So 15 over 35 times 10 gives us, now we did have a minus sign though, so it's minus 4.29 centimeters because the centimeters cancel, leaving only centimeters from there. And that's the image height. Okay, but why is it negative? So these distances are allowed to be positive or negative just like the focal lengths. So in terms of the height being positive or negative, the height is 0 when it's on the center axis. So if the height was positive, the image would be standing upright. If the image is below the axis, it's going to be negative because it's upside down. So the size of it is 4.29 centimeters, but the minus indicates that it's inverted, upside down. Okay. So what that's going to lead us to is into the final part, which is where I ask you what the image description is. But I already told you what the image description was from the ray trace. It was real, it was inverted, and it got smaller or reduced. So how do you use the calculations or the math to determine that we arrive at the same conclusion? So in order to describe the image in part D, label a couple more of these. So part D. Okay. Image description. Okay. So here are the following ways to get the image descriptions using the values that you have rather than the ray trace. So the type of image, okay, real or virtual, remember. So this is what you're going to be using. One of the two options, if di, the image distance, is positive, that means the image is real. If di is negative, that means it's virtual. Okay. So based off of our problem, quickly type in what you think the answer is in this problem, real or virtual. Any ideas? Nobody? Okay, so for this one, if this is the condition for real or virtual, look at the value for di that we got. Okay, so, well, it's inverted, but we're going to look at something else for if it's inverted. So between real and virtual, because the value of di that we got was positive, okay, we know it's real in this case. So remember that this was because we got di was positive 15 centimeters. Okay? So that tells us it's real. Now, you said it was inverted, but now, so the way we determine if it's inverted is based off of what I talked about in the previous part. Okay? So it has to do with the image height or the magnification. So for the orientation of the image, let's call this one 4, let's call this one 5. So for the orientation of the image, if one of the two conditions are met, you can either say magnification or image height. Either one, it doesn't matter. So if the magnification m or the height of the image hi is positive, this implies that it is upright, and vice versa implies that it's inverted. So if the magnification or the image height is negative, it's upside down or inverted. Okay. And as you said, it's inverted, okay, because we got a negative value for hi. So we know it's inverted in our case. 29 centimeters. Okay. Okay. The last thing we need is just the size of the image. Okay. So for image size, so size of image, let's call this 6. If one of the following conditions are met. So for this one, I'm going to do 3 conditions because we have bigger, same, or smaller, basically. So let's say we use the height to do this. So if the absolute value of the image height is greater than the absolute value of the object height, this is a way of saying we don't care about the sign, just is the magnitude, the size of it, larger or smaller. In this case, if the image is larger than the object height, then this implies that the image is going to be upright. I'm sorry, not upright, enlarged or bigger. Okay. The other way of doing this is actually to take the magnification. So I'll write on the side here, the other way of doing this is saying if the magnification, if the absolute value of the magnification is greater than 1. Okay. if you did calculate your magnification, if it's larger than a value of 1 in size, then what it means is it got bigger. So all we do is we just change this to an equal sign if it's the same size. So HI equals HO, then it means same size. Or another way of saying that is the magnitude of the magnification equals 1 rather than greater than 1. And then the last part is if the image height is less than the object height, then that means it's reduced or smaller. And the way of saying that with magnification is the absolute value of m is less than 1. Okay. So in our problem, look at the value of hi, look at the value of ho, and then quickly tell me, is it enlarged, the same size, or reduced based on what we said here? Anyone got a guess for that? Yes, it is reduced. Okay. So because our image height has a value of 4.29 in magnitude, and the object height was 10, it got smaller. So we're going to use reduced. Okay, very good. So notice here at the end of this problem, okay, what you'll see is that when we did the ray trace told us it was real, inverted, and reduced. The math tells us it's real, inverted, and reduced. So the ray trace and the math agree with each other. Okay? So that tells us that our answer is reasonable. Are there any questions on these parts of the problem, anything I have on the whiteboard, or anything in general for the mirrors before we do one last one? And then just give me a thumbs up if everything is good. Got a thumbs up. Okay. So let's take a look at the last one here. Okay. All right, last one here. So 5. This one is kind of a bit further back. All the stuff we did so far is more recent optics, largely, and modern physics. This one is a review of some concepts way back at the beginning. In this one, you have three charges, typo. 3 charges are placed. We have Q1 is positive 5 microcoulombs. I tell you where it's at -7 millimeters. Charge 2 is positive 4 microcoulombs at -4 millimeters. And charge 3 is -3 microcoulombs at positive 5 millimeters. Okay. I give you a figure. In her version of the practice final, she left that out on accident. So this is essentially what you're supposed to have. So now, in a lot of problems, they won't give you this this coordinate system necessarily. They'll a lot of times just tell you the distances between them. which is really what matters here. So I could give you the distance between this charge at -7 and this charge at -4, and then I could give you the distance between -4 and +5. But you could still figure that out pretty easily by just looking at how many numbers separate this on here, just doing the difference between the positions. So we're going to do a couple things in this. In part A, we're going to calculate the net electric field, magnitude and direction, produced at the location of Q1 only due to Q2 and Q3. Okay? So the concept that you want to remember here is that every charge, Q1, Q2, and Q3, all produce their own individual electric fields. That means that there can be up to 3 separate individual electric fields in the problem from each of these 3 charges. But I'm only asking you for the electric field of 2 and 3. So in other words, the charge Q2 at position -4 and charge Q3 at position +5. Okay? Find the net or the total electric field from those 2 charges at the location of Q1. So in the first part of the problem, Q1 all the way on the left side only serves the purpose of identifying a location. We do not actually care about it. We just want to use this location. Okay. What I'll do is I'll draw this up real quick, and let's start with electric fields. Let me switch this. Okay. Do we have any questions on the setup of the problem? Let me know. Otherwise, I will just throw it up here and go further with it. Yeah, you're welcome. No problem. I really enjoy getting to help you all out, and let more people know about this. If you really enjoy this, then tell more people about it, and then get them to come on Sunday. And also revisit my website sometime later today, if not tomorrow, even if you're not doing the live stream tomorrow, because I'm going to put up another poll. And what I want you to do is repeat the same process, go through the poll, list all available times for Monday and Tuesday. So what will happen is we're going to try to do one more review session after tomorrow to finalize before you take the final. So, but yeah, have a good rest of your day. You're welcome. So, let's see here. So for this last problem, let's draw this out. So we have the axis, the coordinate system. Now in my diagram, I tell you it is positive to the right because you can see the negative numbers on the left side and the positive on the right. So it is positive to the right. If it's not given, then a lot of times in these problems, you're just going to make up your own coordinate system. Usually just say like positive to the right. So I'm only going to mark the positions we care about in the problem. So we have a position here. It's x equals -7, and it's in millimeters. Okay. We have another position. It's x equals -4 millimeters. And one last position all the way over here. It's x equals +5 millimeters. Okay. So these are the 3 positions of the 3 charged particles. From left to right, we have that, let me see here, 2 positive charges on the left and a negative charge on the right. Okay. So I'm going to draw this positive charge over here. Now, actually what I'm going to do for this is, despite having drawn all 3 in the diagram, because of the context of the first part of the question, I told you that you're not going to care about charge 1, because we're not going to calculate the electric field from charge 1. We only want to use its location and only use charges 2 and 3 to calculate the electric field. So I have at this middle position -4 millimeters. That's a positive charge. That's Q2. And the right position, is a negative charge, Q3. The values were, and I'll write all the values out. So the values we'll use throughout the problem if we need them is Q1 is positive 5 microcoulombs. Q2 is positive 4 microcoulombs. And Q3 is negative 3 microcoulombs. Okay. Now, recall that the electric field for a point charge is given by this expression, because these are all point charges. So the electric field for a point charge is E equals K Q over R squared. Let's number these. The diagram is 1, the equation is 2. Okay. So K is a constant. It's called Coulomb's constant. Coulomb's constant. Okay. The value is given. Coulomb's constant is 8.99 times 10 to the positive 9. Units are Newton meters squared per Coulomb squared. Now, Q is the charge that we want to find the electric field from. So Q is just the charge in question. And R is the distance from the point of interest that you want to find the electric field at to the charge that you're questioning its electric field for. So R is defined as distance from charge in question to point of interest to find the electric field. Okay. Now, so because in the problem I ask you to find the net, or in other words, the total electric field, it means that you must consider all electric fields that could contribute to it. So in the problem I tell you to find the net electric field from Q2 and from Q3. So what that means is you're going to need to first calculate what E2 is and what E3 is from those two charges. So E2, let's call this 3. So E2 equals K Q2 over, let's call it R2 squared. Okay. Just subscripting everything to say that's all for charge 2. So K we don't worry about, that's just a constant. Q2 is a given value, it's 4 microcoulombs. But then you have to ask, well, what's the distance between the charge and the point of interest that we're calling R2? So in my diagram, the point that we want to find the electric field at is the point on the far left, okay, at x equals -7 millimeters. The charge that I'm using to calculate the electric field for is Q2. That's the charge in question. So what is the distance between the far left point and the charge in question? That's the difference between the position of -7 millimeters and -4 millimeters. So let's say that this distance here is our R2. So R2 is going to be equal to, let me use a different color. R2 equals the difference between these. Let's do absolute value of it because the distance is only going to be absolute value that we need. So absolute value of the difference between -4 millimeters and -7 millimeters. Okay. Just find that difference You could even just eyeball it. It's 7 and 4, so it's 3. So the absolute value is 3 millimeters distance. Okay? That's what we need to use for R2. Okay? So we have that E2, because we have everything now. Let me label this 4, and let me label the next thing 5. Okay. So E2 equals 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. That's the Coulomb constant. Now, the charge is 4 microcoulombs, so 4 times 10 to the minus 6th coulombs. Okay. Divided by the radius, or the distance from charge 2 to the point of interest, is 3 millimeters. So 3 times 10 to the minus 3 meters. And most common mistake here at this point is to forget to square it. So don't forget to square it. Okay. Let's calculate all of this real quick. So 3 times 10 to the minus 3 in the bottom. Don't forget to square. That's on the bottom. Then do it the top across, so 8.99 times 10 to the 9th times 4 times 10 to the minus 6th. Yeah. Minus 3 squared invert times 4 times 10 to this minus 6. Okay. So this one roughly gives us 4 times 10 to the 9th. 4 times 10 to the 9th, roughly. If you look at the units, they're all going to cancel out to newtons if you clean it up, and then coulombs, because it's an electric field. Electric fields are in newtons per coulomb. Another unit you might see on some problems will be volts per meter, and they're the same thing. So we have the electric field from 2, but now we also need to get the electric field for 3. Okay, so we're going to repeat this again for 3. Which means we're going to need the distance for 3 as well. So first of all, E3 equals K Q3 over R3 squared. The distance for 3 is going to be the difference between where charge 3 is and the same point of interest, because we're still calculating the electric field at that same point. So we need to use the positive 5 and the negative 7. The difference between those is going to give us 12. So absolute value of this, you could just do 5 millimeters minus negative 7, and that'll give you the 12. Okay. Let's run the calculation for this, but before I do that, are there any questions on any of the stuff I have on this board before I start erasing from the left side? Let me know, or give me a thumbs up. Okay, let's carry on. So, starting from the left side, let's. I'm going to keep the diagram and let's erase from here, from 2. Okay. So, let's look at this 2. Okay, so now we're just going to plug in this distance into here, and let's just calculate the electric field. So the electric field is going to be E3 equals Coulomb's constant 8.99, 10 to the 9th, Newton meters squared per Coulomb squared, times the charge 3. Now, the charge is negative, but remember, when you're doing these calculations, when you want to find out, okay, what is this electric field equal to? Anytime you're using this to calculate, it's usually preferred that you calculate just the magnitude of it. So we're not really going to care about the sign of the charge because it only has to do with determining the direction of something. So I'm going to take the absolute value of the charge. So in other words, I'm going to use 3 times 10 to the minus 6th coulombs just to get the magnitude of this. Divided by 12 times 10 to the minus 3 meters because of the 12 millimeters. And again, don't forget to square it. Okay. Let's calculate this. So this part, square 12 times 10 to the minus 3. Square that value. It's on the bottom. And then go across 8.99 times 10 to the 9th. And 3 times 10 to the minus 6th. Okay. So this electric field is 1.87 times 10 to the 8th newtons per coulomb. Okay? And that's the magnitude of the electric field only due to charge 3. So again, what was the point of getting this electric field E2 and this electric field E3? The question was, what was the net or the total electric field from Q2 and Q3, which requires that we know both of these. So you have to be careful because these are only the magnitudes. You're not just going to add them. We have to care about the direction. So what we're going to do is we're going to go back to the diagram and we're going to ask what is the direction of those electric fields from each of those charges. So at this location that we found the electric field at, we need to ask for Q2, which way does the electric field point at this point on the far left from there? Remember that for positive charges, so let me write here, recall for positive charges, or let's just say for the direction of the electric field of charges, I'm just going to draw it out. So when you have a positive charge, like a proton or any positive charge, remember that the electric field lines will spread outward and away from the charge in every single direction. So it should look something like this. Okay, that's your electric field for a point charge. That's positive. The negative charge is identical to that picture, except you flip the arrows from going away from the charge to going into the charge in every single direction towards it. So the negative charge is at the center, and the electric field lines or vectors all point inward. Okay. 4 times 10 to the 9th is what I got for the previous one. E2 was 4 times 10 to the 9th newtons per coulomb. I think it was 4 times 10 to the 9th before I erased it. Correct me if it's wrong. So going back to the diagram. So we're going to use the fact that electric fields will point either away or towards the charge to determine the direction. So what we're going to do is we're going to go to point, let's call this point P on the far left side. Okay, so point P. At this point, if we ask what's the electric field from Q2, then we have that if we know the electric field points away from it in every single direction, then the electric field needs to point to the left at this point, to point away from it. Let's call that E2. Okay. Now, for charge 3 here, because it's a negative charge, the electric field needs to point towards it at the same location. So the vector needs to go to the right to point towards that negative charge. So E3 points to the right here. Okay. Notice that E2 and E3 do not point in the same direction in this particular case. In some problems, they could point in the same direction. Some problems, it's going to be in the opposite direction. It's purely based on where the charges are and what kind of charges they are. So you have to go through this every single time you do a different problem. But in this case, because they point in the opposite direction, when you quote-unquote add them together, it's not really going to add them. It's going to oppose each other, so they're actually going to subtract from each other. So we write here, because electric field vectors point in opposite directions when we total them up, they actually subtract. Okay. So the key word here is that they are in opposite directions. Question. So shouldn't the charge for Q3 be negative? So, okay, so if you're referring to point number 2 here, then the charge is negative, but remember we're not going to plug in minus because it's only going to tell us something about direction. We only want how big it is, the magnitude of it for now. So let me write here that this right here, ignoring plus or minus because only want magnitude of E3. Okay? Same goes for E2. But once you get the magnitudes, which are always positive, you handle the directions separately. Okay? It's easier to handle the directions separately in these problems. In other words, the way I handled it here was to conceptualize, do the electric field lines go away or toward a charge? So then all I do is I go back to the diagram and I say, does it point this way or does it point that way in order to go towards a charge or to go away from a charge? In our case, it was away for E2, to the left to go away from Q2, and E3 was to the right to go towards Q3, which was negative. So where you actually account for the fact that it's negative is not when you calculate it, but when you conceptualize it to draw the vector, if that makes sense. Yeah. Okay, so we're good. Now, let's wrap this up, okay? We're going to subtract E3 and E2. Specifically, notice that E3 points to the right in the positive x direction, and E2 points in the negative x direction. So what you're going to do is you're going to do positive E3 and negative E2. So in other words, the net, or the total electric field, equals E3 positive. If you want to write it this way, you can write plus negative E2 to emphasize the fact that it points to the left in your coordinate system. So that's why you're ultimately subtracting. Take E3, which was 1.87 times 10 to the 8th newtons per coulomb, and subtract off E2, which we got previously, was 4 times 10 to the 9th newtons per coulomb. Okay. Notice that because E2 is larger than E3, because E2 is 10 to the 9th, E3 is 10 to the 8th, which is smaller. You have a bigger negative number than you do a positive number. So you're going to get a negative answer, which indicates that it points in a certain direction. In this case, 1.87 times 10 to the 8th minus the second value, 4 times 10 to the 9th. That gives us an answer of negative 3.8 3.81 times 10 to the 9th newtons per Coulomb. Okay. So this right here is your answer to this part of the problem. This tells us actually both the direction and the magnitude in one shot, because the magnitude of it, let me do this in a different color to indicate the magnitude. The magnitude is 3.81 times 10 to the 9th newtons per Coulomb. Okay, so magnitude. The direction of this is indicated, let me do a different color again. The direction of this is indicated by the minus sign. Okay? This comes from the fact that one was bigger than the other and we subtracted the two to get them going in different directions. So if the answer is negative, this means the net electric field points in the negative x direction. Okay. Are there any questions on this before we wrap it up and I erase this? Give me a thumbs up if we're good, and then we will wrap it up. So there's one question. Did you do E3 plus negative E2 because E2 is going to the left? Yes, that is correct. You do positive E3 because it's going to the right, which is positive in our coordinate system. And you do negative E2 because it's going to the left in the same coordinate system. Okay. Any other questions? Otherwise, just give me a thumbs up and we'll do the last part, which is actually pretty quick. This is most of the problem. Let me also number these real quick, just for ease. 3, 4, 5, 6. Okay. I'm going to erase the left half, and let's look at the last part. Okay. Last part of this is to calculate the net electric force, magnitude and direction again, acting on Q1. Okay, so you could do something here, which is what you might be very familiar with, which is to use Coulomb's law, because I asked you for the net electric force. But if you do that, you're going to spend the same exact amount of time that we've spent so far trying to get an answer that shouldn't actually be that long. Notice that because I asked you for an electric field in part A, since you already know what the electric field is, you can relate the force to the electric field using a very simple equation. Okay, so in this diagram, being very specific, notice that we have a charge Q1 at x equals -7. Okay, we did not even consider that in the first part, simply because I only wanted to use its location. I only wanted the electric field from 2 and 3. In this part, I do want the force on Q1, so I am going to consider it now. But how it's going to work is use this simple concept. Any given charge will only feel the effects of other charges. It will not feel the effects of itself. In other words, Q1 cannot apply a force because of itself, to move itself. Q1 will only feel forces from Q2 and Q3. So let me go back over to here and let me emphasize this. I realized I erased the net electric field. I believe it was -3.81 10 to the 9th. Confirm or deny that. So I'm going to use a very simple equation here. take that out. Okay. So negative 3.110 to the 9th. Okay, good. So the force on charge 1 equals charge 1, so you will use its own charge, times the electric field total. Okay. This specifically is referring to the total electric field at the location of Q1. Okay. This equation on any formula sheet is literally just F equals QE. Okay. It's a very simple equation. But this is how you interpret it, is if you want to find the force on any given charge, you want to find it by using the charge that you're asking for the force on and multiplying it by the electric field it feels from the other remaining charges. So since we already have that, all we have to do is just plug it in. So equals, now if you want to just get its magnitude, you can just take the absolute value of everything. If you want to get the direction of everything, by calculating it, you will account for the signs. It's completely up to you. I'll show it with the signs. So for instance, we have a positive charge at that location, Q1, and that charge was equal to a value of 5 microcoulombs positive, so 5 times 10 to the minus 6th coulombs, times the electric field we found previously, which was magnitude and direction minus 3.1 times 10 to the 9th newtons per coulomb. Okay. If we just calculate that with plus and minus signs on everything as needed, it will give us the magnitude and the direction. So, oh, the value was 3.81. I don't know if I wrote that, but it's 3.81. I had it in my calculator. Okay. If I wrote 3.1 previously, it's 3.81. Equals times 5 times 10 to the minus 6th. So the force acting on charge 1 from Q2 and Q3 is negative 1.91 times 10 to the 4th newtons. Okay. Notice the coulombs cancel out and you get a force in newtons. So what this means is the total force has a magnitude of 1.91 times 10 to the 4th newtons, and the minus indicates it's to the left. So again, minus indicates to the left. Okay. All right. And that wraps up the whole thing. So are there any last questions on this problem before we wrap up? It's all good. It happens. What were the directions of Q2 and Q3 again? If you're talking about the directions of something, in this case it's the directions of the electric field. The directions of the electric field were to the left for E2 and to the right for E3 because E2 was going away from a positive charge to the left and E3 is going towards a negative charge, so it's to the right. Those are the individual directions, and based on our calculations, so when we got the net electric field was negative 3.81 times 10 to the 9th newtons per coulomb. The minus sign indicates that the total electric field is to the left. Okay, so then that's the direction of the entire electric field from Q2 and Q3. Cool. Good, good. All right, any last questions on this problem? Okay. If besides that, so what I'm going to do is, again, revisit my website sometime by this evening, I would say. If not, tomorrow morning. You'll find a poll link posted sometime by then. And list all the times on Monday and Tuesday that you are free to continue doing more reviewing, besides the time on Sunday that we have planned, which is listed also on my website. And we'll take it from there. And what I'll do is I'll also tell you when you need to complete the poll by, so that we can lay out the times for Monday and Tuesday ahead of time. So, and I'll make either more problems that are similar to the practice test that she made, or we will just go over her practice test entirely, basically. So one or the other. So with that, no last questions. Would you be able to explain the uncertainty equation next time? If you're talking about the uncertainty principle, yes, we can do that. I can even include some stuff that will calculate and deal conceptually with the uncertainty principle. If you want to, so you can email me any individual things you have. Otherwise, actually, I'll put an email on my website that you can just send stuff to if you don't already have it. You can ask me any questions, tell me anything you want to see on the next video that you want more emphasis on, and we'll review those concepts. So yeah, how momentum and why and uncertainty work together. Yeah, we'll definitely do more of that then. Yeah, you're welcome. So thank you all for tuning in. Let your friends know. And if you like what I'm doing, then letting other people know is going to help me to continue to grow to help others. But also, if you want to donate, there's a link on my website too. What I'm doing is completely free because I know we're all college students. But if you have a little bit to spare, it'll help to keep me going. So you don't have to, but notice it's there. So thank you very much. Peace.